Okay, so we will continue our discussion of how to incorporate dispersive materials into FDTD. So far what we did was we started with the Debye model, and one thing I want to clarify is that every E cell has its own value of epsilon r. Okay. So, this has to be kept in mind in the data structures. You need to have a elaborate data structure that stores. So, for example, what all numbers will you have to store? For every E cell, you will have to store epsilon infinity, epsilon s and tau. Okay, these are three, it is a 3 parameter model. So, okay, so what we did was we took this Debye model, we took its inverse Fourier transform and substituted it into the relation for D to obtain D in the time domain. Once I get D in the time domain, I can take finite differences and use Maxwell's equations over here. The whole reason that we were trying to do this is somehow we want to avoid having to store the entire field history, right. Right now the expression that I have over here, this expression does not avoid that, because electric field for all the past time instances is still being stored. Okay. So, let us see now what we can do with this expression. Okay. So, what follows now is little bit of algebra only. Okay. Now, to make this whole math a little bit easier, I am going to define a new auxiliary variable. Okay. So, this entire summation over here that you see, okay, I am going to call it by a new variable phi n minus 1 just for convenience. Okay. And then what I can do is, in an update equation, what do I want? I want a relation for E n in terms of everything else. That has been the philosophy of FDTD, right. So, this d n minus 1, I am not interested in d, I want relation between E and h. So, I use Maxwell's equations, and what should I replace this by? So, this is d n minus 1, it should get replaced by curl of h and a delta t, right. So, this should be equal to delta t times curl of h n minus half, right, since it is just the difference d n minus d n. So, from this entire expression I can extract, what do I want to extract? E n. I want a relation for E n in terms of all past electric field and magnetic field. So, can I do that? I can. How many in this expression over here, how many places does E n appear? 1, 2, 3 or many times? Only once, because the summation never reaches, the m summation never reaches E n. So, I can pull out E n on one side, move everything else to the right hand side, right. So, this is a fairly simple manipulation. So, I will move this epsilon naught, epsilon infinity to the right hand side. So, I will write down the final expression that you get. There will be a beta naught bar also. So, you can see part of the reason why I introduced this capital psi, just to make this expression look a little bit compact, otherwise it will look very ugly. Okay. So, from the FDTD philosophy, I have, let us say, present, and this whole thing is past. So, the philosophy in FDTD has been use the past to get to the present, okay, and time step. Okay. So, still this is not something I can implement on in code, because the term over here which is very difficult for me is this guy, psi n minus 1, right. Psi n minus 1 is has the sum of all past electric fields, which I do not want. So, now Let's try a little bit more of algebra to see how we can simplify things further. Okay. So, let us see, okay, still need that is what we need. So, in psi n minus 1, you notice that there is a beta bar m plus 1 minus beta bar m, correct, this expression over here. So, I am going to call this term over here as another, there are many simplifications that we need to do. So, I am going to call this delta beta m. Why is it psi of n minus 1 you mean? That is psi bar, yeah, that is not minus, yeah, that's it is not minus n minus 1. So, what was our expression? Psi n minus 1 was a summation of m is equal to 0 to n minus 2, okay. Then I had a E n minus 1 minus m, and I had a delta beta m, okay, and this delta beta m was, yeah. So, this delta beta m, we wrote it as this beta bar m plus 1 minus beta bar of m, okay. And now I need to substitute the definition of beta bar. So, what was beta bar? If you remember over here, I think we had defined it over here, right, this in the green font. Beta bar m was the integral of beta over one time instant, right. So, let us just use the definition of this beta bar. So, this will be integral from, so this integral will be from which time instant to which time instant? M plus 1, right. So, m plus 1 delta t to m plus 2 delta t, and I am going to have a beta t dt. Similarly, m delta t to m plus 1 delta t beta t dt, okay. And what we need to use? The expression for beta t. We know the expression for beta t, right. We had taken the inverse Fourier transform, we had got a exponential multiplied by a step function, right. So, our beta t expression, which I will just write down from earlier, was epsilon s minus epsilon infinity by tau, and the exponential. So, does this look like an integral that I can do? Looks straightforward, right, does not look very complicated at all, okay. So, it is just an exponential, right. So, I can integrate it. How many terms do you expect will happen? 4 terms. Each exponential, when I integrate, I will get an exponential. The limits will give me two terms, and there will be one common m plus 1, right. So, I should expect 3 terms, right, in the when I evaluate this integral. Okay. This is just to anticipate what happens. So, this expression, let me write it. So, I get a minus tau. So, there is this epsilon s minus epsilon infinity by tau was already there in the definition of beta t. Then when I integrate e to the minus t by tau, I get a minus 1 by tau. So, that is a minus tau over there, and I should get 3 terms, okay. What will be common to all of these 3 terms will be e to the minus m delta t by tau, right. So, I can write this as 1 minus 2 . Okay. So, let us do a quick check. M plus 2 delta t, is that term there? Right. So, if I take this guy and this guy, I get m plus 2 times delta t by tau, that is coming from this first guy. Then m plus 1 delta t should come 2 times, right. So, that is coming over here, and the final term is m delta t, that is coming here. So, I have taken care of all 4 terms combined into 3 terms. Okay. So, this is delta. So, what after all doing all of this, what is interesting to note is where is m appearing in this expression? I have so many terms, but m is appearing only in only one term over here. This is the only place where m appears, right. So, in other words, if I look at this, if I look at delta beta m, the m term is only appearing here. Supposing I want to calculate delta beta m plus 1, then what will happen? There will only be m plus 1. So, what do these delta betas resemble? What kind of series does it look like? Geometric progression. Every term is obtained by multiplying just one constant term to it, right. So, in other words, these delta beta m's resemble a geometric progression, and that is a thing that is going to help us a lot, because we know that the ratio of consecutive terms of a GP is constant, right, independent of m. So, if I look at delta beta m plus 1 divided by delta beta m, what should this ratio be? Yeah, m should not be there. Okay. So, now I can write down the expression for psi n minus 1. Okay. I can write it as, so let us write it, let us split this summation. I have m is equal to 0 to n minus 2. So, I want to utilize this, this observation that I have over here. So, what I am going to do, a small trick, I am going to split this summation keeping the first term. So, what will be the very first term? M equal to 0. So, m equal to 0 will give me e to the power, e n minus 1 delta beta 0. The next summation I will keep as is, m is equal to 1 to n minus 2, right, and the same terms n minus 1 minus m delta beta m. I have not done anything great so far. Okay. Now, in this summation what I can do is, I can introduce a new summation variable instead of, see this in the summation for psi n minus 1, my m is going from 0 to something, and the way that I have written it over here now, m is going from 1 to something. If I want to bring it back down to 0, I need to introduce a new variable. So, let us call it p, such that m minus 1 is equal to p, right. So, m minus 1 is equal to p. Okay. So, with that what happens to this summation is, this will become summation of p is equal to 0 to, p is equal to 0 to what? N minus 3, okay, and this will become e n minus 2 minus p, and this will become delta beta, not p, p plus 1. And now I'm in a position to use this trick, right, this guy over here. So, what will happen to this guy? This will become equal to, now delta beta p plus 1 can be written in terms of delta beta p. Okay. So, this will become p is equal to 0 to n minus 3 e n minus 2 minus p delta beta p and e to the minus delta t by tau. Okay. So, this term can be taken outside the summation since it does not depend on p, right. So, this guy can be taken out over here. Okay. Now, as the final step, I can go back to my, supposing I go back to my, well, I do not need to go back. So, now over here I can replace, I need not replace it. So, what does my expression become? So, e n minus 1 delta beta 0, okay, plus e to the minus delta t by tau, that was the common term, and a summation p is equal to 0 to n minus 3 e n minus 2 minus p delta beta p. This is my psi of n minus 1. Okay. Does anyone recognize what this expression on the right looks like? Particularly this expression. Look at this expression and this expression. Is there something common? It's psi of n minus 2. In the upper expression, if I replace n by n minus 1, what will happen? Left hand side will become psi of n minus 2, the summation will become n minus 3 and e will become e n minus 2 minus m, and whether it's p or m is just a dummy variable, right. So, this expression that I have over here is nothing but psi of psi n minus 2. Right. So, in other words, this has become e n minus 1 delta beta 0. Let us write it out. Right. Is it clear what we did? And what was key to this was the geometric progression. It allowed me to just remove one term and make it look like the previous term psi n minus 2. Okay, so let us write down this final expression once again and then we can see the implications of it. So, I have psi of n minus 1, which is what I wanted, that became e n minus 1 beta delta beta 0, right, and then I had e to the minus delta t by tau psi of n minus 2. Okay. And remember, our expression, our update equation was this guy. And which is where we went to simplify the psi n minus 1. So, after doing all of this algebra, what have we gained? So, when I look at this expression, I needed psi to evaluate psi n minus 1, I needed all past electric fields. Now, when I look at this expression, has something changed? One past and one and one psi also, yeah. So, is that an improvement? Yeah. So, I don't need to store all the electric fields, but I need to store one new variable which is psi. To evaluate psi at n minus 1, I only need psi n minus 2, I do not need psi n minus 3, 4, 5 up to psi 0. No, so see, so far what was, okay, so far we were storing, what all were we storing? We were storing the e's and the h at space and time grids. Now, what we have to do? E, h and psi at space time grids. So, I have my computational load has increased by one more variable that I have to store. Now, if I initialize this psi properly, then every time I want to evaluate psi, I just need one past value. It's just like the electric field update. I need one past value of electric field, one past value of magnetic field to get the current E and H. Same thing is happening now. My price is store one more auxiliary variable, right. So, the plus point is no need to store entire history. Of E and H, and the minus point is store one new auxiliary variable, which is Yeah. Well, once you initialize it, so I mean you have the definition of psi over here, right? So you can see psi n minus 1. So for example, yes. So I will use, there's an so this is your update equation for psi. Yeah, well, how do I, his question is how do I get psi in the first place? Yeah, so to get psi in the first place, I need electric fields and this expression over here in the green arrow. Once I get it once, then I am done. Then I need to use this equation, right. So you can call this the, instead of update, we can call this the initialization equation for psi, and then this becomes the update equation for psi. Okay. So what we have done as a result of this is we have reduced a convolution integral to a running sum. Okay. Did we do any approximations to arrive at this? No. So this is as accurate as if you wanted to store all the electric field histories. There is no approximation made in going from electric field history from convolution to this running summation. Okay. So the only price we had to pay is store one new variable, and of course so this was, the assumption was a Debye model. Okay. There are other kinds of resonances possible. So for example, there are others are more general are Lorentzian resonances. So in fact, the Griffiths reference which I gave you derives a Lorentzian resonance. So they have their own update equations to get, I mean they have their own algebra to get an update equation, but we won't deal with that in this development. Okay. So I think this is a sort of a good point to tell you about, introduce at least the name to you. There is a popular open source software in which you can solve FDTD equations. Okay, it's written for 1D, 2D, 3D. It's called MEEP. Okay, this is by the ab initio group at MIT, where I mean it's a very flexible and it's open source. So you can go in and see how they have implemented various update equations and all, and it can handle of quite a variety of different resonances. Okay, so I mean it's used extensively for research purposes. So just Google this name and you will find out how to do it. Okay, it's written in the basic language in which they have implemented it is something which is not very common. Okay, it's a very peculiar language called Scheme. Okay, it's not a compiled language. So unlike C or C++, it's not that you compile it and then run it. It's like a little bit like Python, right? You just go step by step, interpretable, right? They also have a C++ interface if you wanted speed. Okay, so have a look at this.